Afternoon, everyone, and welcome to today's webinar, Direct Estimation Methods in the National Crime Victimization Survey, hosted by the Bureau of Justice Statistics. At this time, it's my pleasure to introduce Alexandra Thompson, statistician with the Bureau of Justice Statistics, for some welcoming remarks and to begin the presentation. Alexandra?
Thank you, Daryl, for that introduction to the webinar, and welcome everyone again. My name is Alexandra, or Lexi Thompson. I'm a statistician in the Victimization Statistics Unit at the Bureau of Justice Statistics. My portfolio of work currently focuses on school of crime, hate crime, and victim service providers. I've also co-authored various BJS statistical reports, including Criminal Victimization 2021 and Hate Crime Victimization 2005 to 2019. With me today, we also have Dr. Erica Harrell, who's also a statistician in the Victimization Statistics Unit at BJS. During her tenure at BJS, she's written on a variety of topics, including workplace violence, identity theft, and crimes against persons with disabilities. She was also part of the BJS team that created the NDASH, the data analysis and visualization tool that generates estimates using data from the National Crime Victimization Survey. We also have Dr. Marcus Brzozowski from RTI International, where he's a senior research statistician. He has over 20 years of experience with design, implementing, and analyzing complex survey data. For the past 10 years, he has served as the co-principal investigator on the National Victimization Statistical Support Program, which he has helped BJS review and improve methodology used for the NCVS. Dr. Brzozowski has also authored several federal and peer-reviewed publications on NCVS methodology, including reports on producing direct variance estimates with NCVS data. We also have Andrew Moore available, who is a research statistician at RTI International for 14 years, where he has experience with survey research. His areas of interest also include implementation, weighting, data analysis, and SAS programming. For the past 10 years, he has served as a statistical task leader on the National Victimization Statistical Support Program, where he has contributed to numerous substantive and methodological tasks aimed at enhancing the NCVS. I'll now go over the agenda for today's webinar. We'll start with learning about what variance estimation is and why it's important. Then we'll go over the differences between direct and indirect variance estimation, including the methods that are listed below on the slide. We also have two demos on direct estimation, one in SAS and one in SPSS. And as Daryl mentioned, we'll have a Q&A at the end of the webinar. And I'll start us off today by talking about what variance estimation is and why it's important. Before I talk about the exact definition of variance estimation, I want to talk about the structure of the NCVS, because that's related to how we approach variance estimation for the data. The NCVS is a survey where we interview a sample of households that are representative for the entire country. This map gives somewhat of a visual representation of that. These points are not based on NCVS data. They are randomly generated, but we're not a census of crime across the country. We interview a sample of persons within a sample of households. And since it's not a complete count of crimes that occurred across the country, we need the data from the households that we interview represent not only themselves, but also the households we're not able to interview through the NCVS. And we're able to generate national estimates for crime across the US, partially through weighting the data. And so what is variance? Estimates based on a survey and based on a sample have some degree of sampling error. And sampling error can depend on a variety of factors, including the amount of variation between responses for similar households and also the size of a sample. So if you have a small sample for a particular group, your sampling error may be larger, and for a larger sample, your sampling error may be smaller. And the variance which we're talking about today is a type of sampling error. and that measures the deviation between the estimate that we have from the survey and an average. This theoretical average comes from the idea of if we did this survey with different samples over and over and over again, there would be an sort of a true average between all these different estimates. So the variance is measuring the deviation from our current estimate compared to this theoretical average. And then the standard error, which you may have heard about before, is the square root of the variance. And standard errors can be used to calculate confidence intervals around an estimate. You may have heard of, a 95% confidence interval. This is a visual representation of a confidence interval. This screenshot comes from the NCVS dashboard, or NDash. And so the blue trend line represents the estimate or the rate of violent victimizations per 1,000 persons aged 12 or older. The brownish shaded area represents the confidence, the 95% confidence interval around the estimate. So that top brownish line in the white is the upper bound, and then the brownish line in the blue area, that is the lower bound of the confidence interval. So for example, in 2021, we estimated that the rate of violent victimization was 16.5 violent victimizations per 1,000 persons aged 12 or older. And then we estimated a standard error using GBS that was about 0.82. And using that standard error, we calculated the confidence interval that is displayed on screen. And so another way to interpret this is if BGS used the same sampling method to select different samples and compute an estimate for each sample, it would expect the true rate of violent victimization to fall between 14.86 and 18.08, 95% of the time. Now, why is this important, calculating the variance? It gives you partially an idea of how reliable your estimate is. An estimate with a smaller standard error, which is the square root of the variance, provides a more accurate or more reliable approximation of this true value than an estimate with a larger standard error. And so larger standard errors may have less precision and less reliability. And then depending on the parameters of your project, an estimate with a very large standard error should usually be interpreted with caution and also may not be usable. Standard errors also help us determine whether two estimates are statistically different or not statistically different. For example, you can have two estimates where one may be technically higher than the other, such as maybe you have one estimate of 16.5 and one estimate of 17, whether that's a rate or a count. And so 17 is technically higher than 16.5, but when taking into account these standard errors, they may actually not be statistically different. And so in a lot of BGS reports that you'll see, or for every BGS report, we conduct statistical tests to determine whether our estimated counts, percentages, or rates, whether they were statistically significant compared to maybe another estimate once the standard error is taken into account. Also with variance estimation, it's important to account for the NCVS's complex sample design. And if you don't account for the design of the survey, then you may underestimate your variance, which could lead to inaccurate confidence intervals or inaccurate statistical comparisons. And that's done through weighting, the weights that are present on the data file for the survey, and also some other variables which Marcus will go into during his portion of the presentation. Speaking of Marcus, I'll turn it over to him to talk about types of variance estimation.
Thanks, Lexi. Good afternoon, everyone. I'm Marcus Brzezowski. I will talk about types of variance estimation and sort of compare the different, give advantages and disadvantages of the different types. And then I will also give the example in SAS. So with that, for variance estimation, there are two broad types. there's what's called direct variance estimation and indirect variance estimation. Direct, and we'll define each in the forthcoming slides, but direct estimation often can come into two different flavors. One is called Taylor series linearization, and the other are replication methods. And then there are several different types of replication methods, and I'll talk about the one that the NCVS uses in particular. On the indirect side, the indirect estimation, the main type of estimation is called a generalized variance function. There are other types of indirect estimation. So for those that have heard of like small area estimation, that is a type of indirect estimation, but that's a very different type, a very specific type of indirect estimation. But the main one for just a general data set like the NCVS that can produce estimates for any type of estimate is called the generalized variance function. We'll talk about that coming up. So we will start with indirect variance estimation. So how does indirect variance estimation compute a variance? Well, the generalized variance function, often abbreviated to be GVF, is produced through a nonlinear model, and I'll show you what we mean by a nonlinear model in a second. And so this nonlinear model is used to fit the variance estimate. So it's a linear model where the outcome are the actual estimates produced through direct variance estimation. That's your outcome for the model, and then it has this nonlinear function that is used to then model what the variances are and produce the regression curve that then produces the variance estimates from the GVF. Once you have that model, so someone else creates that model, you don't have to create that model. Someone else produces that model. Once you have that, then there will be some model parameters. So just like in a model, there's their beta estimates. So those beta estimates are then model parameters that are given to you that you can then plug into a very relatively simple function that you can use in Excel or whatever. And then that will then generate with some totals that you can get out of the data. You can then generate your standard errors. So in terms of needing anything special, no. So no special software is needed. In fact, you could use a SAS or an SPSS just to generate to summarize the data to get the necessary population counts or counts that you need to input into the formula. But really, even if you just had the data it would be a little hard, but if you had the data in an Excel spreadsheet, you could just summarize it in there. So you don't really need special software per se. I mean, it can make your life a little easier, but you don't actually need anything special. And so that's one thing that's really nice about GVFs. And with that, only the weighted estimates and the model parameters are needed, as I just said. And everything in theory could be done in Excel, but it's certainly having a software like a SAS or SPSS just to summarize stuff will make your life a little easier. Looking at the basics of it, so I wanted to I don't want to get into the nitty-gritty of these formulas. I know they're a little complicated looking here on the left side, but I just wanted to show you what is meant by a nonlinear function. And basically, a nonlinear function by definition just means it has things like a square or a square root, and it's just not going to produce a straight line. So basically, when you produce variances for any data set, they're not going to come out in a simple straight regression line. That's simply a straight line that you could fit to that curve. It's going to be some sort of curve or some sort of different shape. And so you need a nonlinear function to describe that pattern. And so in the NCVS, there is relatively complex, and there are different patterns depending on the type of estimate. So for a total, there's what's called a 3-parameter model. So there's 3 parameters. There's this A parameter, the B parameter, and the C parameter. And so when you're using the GVF, you would have an A parameter, B parameter, C parameter. You just basically enter those into the function along with your totals that you get from the data, and you would then it would then give you the variance for that estimate, and then you can take the square root of that to get the standard error. The function is different if you're producing a rate per 1,000 persons or households. It's a 2-parameter model with just the B and the C parameter and a slightly different function. But so basically you can get these values of T or R or N. Those come directly from the data. You then enter those, and then with the parameters that are given to you in a spreadsheet, you can then just enter them and get your variance. So it's a really relatively straightforward thing to implement for a single estimate. If you're doing a lot of estimates, it can be a little cumbersome, but in general, for a single estimate, it's a relatively straightforward approach to calculating variances. But I do want to point out that it's an approximation because it's a model. It's not getting the exact variance for a certain outcome, but it's the model approximation of that variance estimate. So turning to then direct variance, to contrast to direct variance estimation. So how does it compute variances? Well, it computes it directly from the data. So it pulls in the data and it will directly compute the variance estimation based on the actual individual, case level data. It doesn't, and as such, it doesn't require outside information. Everything you need to calculate the variances are on the, or should be on the data set that you're using for analysis. So in terms of then what's special that's needed, you do need, but with that said, you do need to have certain variables on the data set in order to calculate the variance of a complex survey design. And they're usually one of two types of variables, and we'll talk about that. And it depends what variables they are will depend on the type of direct variance estimation you're going to compute. And I will talk about that as we talk about Taylor series or replication in a second, because which one you need is various. I'll talk about that in a second, but what variables you need will depend on the type of direct variance estimation you need. And to do it, to get the proper standard errors, you do need a statistical software like SAS, SPSS, Sudan, or R. All of those will have survey packages, complex survey packages that can account for the complex survey design when computing the variances. And these packages are important because regular SAS, base SAS, or base SPSS, they will not calculate the correct standard error because there are weights and populations, they will underestimate your standard errors. So if you're not using a complex survey package in one of these software packages, you will get incorrect standard errors. So you need to be very conscious of that, because you could just have base SAS or base SPSS and run a function and get a variance. But that if you're using complex survey data, that variance will be wrong. It'll be smaller than it should be. And so you need to make sure you're using the complex survey functions or procedures when using these software packages. Okay, and we'll talk about the SAS example and SPSS later in the presentation. So the two types of direct variance estimation that I mentioned a couple slides ago are Taylor series linearization and replication. I'm not going to get into the nitty-gritty of how those two approaches work, but I'll just simply say what is needed to operate them from a practical standpoint. For Taylor series does rely on the design, the survey design. So you need to be able to specify the survey design, and with that, you need two things. You need the population weight, which is the main weight on the file, and then you need to be able to define the design parameters, which often are a stratification variable or a clustering variable, often called a PSU, primary sampling unit. These variables will be on the survey file, on the analysis file, and you need to specify them in your statistical procedure. Replication, when it produces, it accounts for the design, and so you do not actually need the design parameters. You need the population weight, but instead of the design variables, you have a set of replicate weights. So replicate weights are basically it's dropping some cases, creating a variance, and then doing it again and over again, so that it captures the variation in the underlying sample data. And so one nice thing about replication is that you don't need to know or specify what the design was. You don't need to have that information, but you do have this series of replicate weights. So for example, the NCVS in the last 20 years, I think it has sometimes been different, but there are 160 replicate weights on the file. So it's not a small number of additional variables that you need to specify. So anyway, so there are different ways of doing replication. It's just the different ways of creating those replicate weights. Main ones out there are jackknife or delete a group to delete one jackknife, and then balanced repeated replication, or BRR. And the NCVS uses that second one, balanced repeated replication. And so it uses that approach to create the replicate weights. And that's important, and you will need to specify that in the sampling procedure. And the NCVS, in fact, uses a special version of BRR called phase BRR, so for Bob Fay. So in terms of some basics on Taylor series linearizations, in terms of how to use it, you do, as I mentioned, need to know the design variables, and there are two such variables on the NCVS. So the pseudo strata, which is, if you're using the public use file, the V2117, and then the half sample variable, which is V2118, and that's the clustering variable. And then there are the NCVS weight variables. There are three, depending on which file you're using. The weight Percy, weight HHCY for the household weight, and then the incident weight, which is weight Vicky times, we in most cases multiply that by the series weight. So if it's a series incident, that will inflate the victimization weight. As I'll talk about, you only can use one population weight at a time. So we'll talk about how you take the three files that are the NCVS and create a file that can be used for direct variance estimation. For both Taylor series and replication, you'll need to do some data manipulation to get to combine the incident file with the person or household file to get it to in a way that can then run in a statistical software package. And I'll talk about that when I get to the example section. Okay, BRR basics. So you have the same population weights there below, but above, instead of specifying the design, you have the replicate weights, and there are two replicate weights on the household file and replicate weights on the person file that you will need. One thing I'll note is that these replicate weights are, for those that are familiar with the public use files in the NCVS, these replicate weights are only available on the single year annual files. They're not, for those that are used to downloading the concatenated file that already has a lot of years set together, that will not have the BRR weights. So if you want to use BRR, you need to download each individual file and then stack them together and use them that way. The other thing I'll just note about for both direct variance estimation methods, so the NCVS every 10 years changes to a new set of primary sampling, a new set of clusters, a new set of primary sampling units to take into account the new census. And so when that happens, the definitions of the design variables will change. And so that you just need to know that and add an extra variable sometimes in your analysis, in your design specification. The replicate weights in the single year weights should be fine, but it's probably more of an issue with Taylor series. But I'll just note that they don't actually show that in an example, but I thought I would note that because that's an important detail. Looking now, so that's sort of the basics of each of these methods. And now I thought I would just spend the next few slides sort of just doing some comparing and contrasting of the different methods. I know some of this text is small. I didn't know how to get it bigger, but I wanted just to sort, because there's no perfect method. There's no like, oh, if one question out there is like, well, if you had to do one way, which would it be? And it really is your user preference, to be frank. So but you should know the advantages and disadvantages of each. And so first I'll just compare indirect to direct, and then we'll look at comparison of BRR to Taylor series. But looking at indirect to direct, some advantages, and some of this is repeating things I've said, but looking at indirect, you don't need to know how to use a complex survey package. So if you're not program oriented, as that's not your thing, GVFs are really nice because they allow you to get the correct standard errors without having to learn a software package or even get a software package. So that's nice. And then and it doesn't really require any file manipulation, which I just sort of mentioned that you have to do with both the direct estimations. You can leave the three files as they are, get the necessary counts that you need from the respective files for whatever estimate you're producing, and then plug them into the formula. On the disadvantage side, they are less accurate. It's a model-based approach to producing estimates, so it is an approximation rather than exact standard error for a specific estimate for a specific outcome. And it has to be calculated for each outcome individually. So you're going through each one and calculating it one at a time. And if you're comparing years, there are additional parameters I didn't mention. There are correlations because the NCVS in particular, it's a rotating panel design. So households are in the sample for 3.5 years. And so each year there's repetition in the household. So there's a correlation there in the samples. And so you need to account for that correlation. And so there are additional parameters that the Census Bureau provides and BJS provides, that if you're doing a year-to-year comparison, you want to make sure you take into account. Again, not anything you can't do in a spreadsheet, but just more things that you just need to be aware of and make sure you are taking into account. Whereas on the direct side, some advantages there that, again, they're more accurate. They're specific, using the data specifically for that outcome that you're estimating. You can estimate in a statistical procedure, you can list multiple outcomes simultaneously, get multiple outcomes, look at domain estimates simultaneously, do all that all in one fell swoop. So estimates can be done a lot more quickly. And so, which is good. And you can do comparisons over time as well. I mean, so the statistical complex design package will take into account that correlation that I just mentioned. You don't need to require to do anything special to do that. Some disadvantages are, though, if you are not, programming is not your forte, there's one, access to those software packages, and then two, knowing how to use them properly, which that's, that can be certainly a barrier to some people. So the GBFs are nice because I think it doesn't require that barrier. And just to know, these are quirks specific to the NCVS. There are some quirks to both methods. Neither method is perfect. So when it comes to the NCVS data, unfortunately. So for example, 2016 in particular was a weird year. That was a year where they were switching over from the census data, and they were doing and the design change. They expanded the design to allow for state level estimation. So there are a lot of changes going on. And at that point, they had to modify the design variable. So Taylor series is that actually not an option for 2016. So if your analysis includes 2016 and you want to do Taylor series, you're not going to be able to. Whereas on the flip side, BRR can be done for 2016. It can be done for all years. But in SPSS, if you're not like a super SPSS user, the complex package in SPSS will only do Taylor series. To do BRR, you can do it, but you have to write your own macro. There's no default BRR option in SPSS. So it can be done, but it does require a macro that you write to basically to program the BRR function yourself. And so that, if you're not, again, an expert SPSS function, that could be a barrier. But once you have that macro, once you have that function, then yes, you could do BRR in SPSS without any issue, and you can do it for all years as well. And as I said earlier, when we'll talk about this, there is some file manipulation required because you can't separately analyze the incident file and the household or person file. You have to combine the incident to those files, and then once the incidents are appended or merged onto the person or household file, then you can analyze, calculate direct variance estimates. Now, just focusing on the two direct variance estimations now, Taylor series here on the top and BRR on the bottom. There are some differences. Taylor series is computationally faster technically. In today's day and age, what does that mean? I mean, BRR, maybe it takes a couple minutes longer depending on the memory of your computer. Computers today are all pretty good. So I mean, that is a true statement, but in today's world, I don't think it's a major barrier with BRR. But it is, but Taylor series is technically will run faster. And Taylor series is easier to run in SPSS. If you're an SPSS user, Taylor series is definitely, it's default, it's the only complex estimation procedure, base procedure in the complex design. Like I said, you can write a macro to do BRR, but if you don't have that, Taylor series is much easier to implement. And Taylor series is easier to implement across decennial census if the number of replicates change. So the last couple decennial censuses, the BRR number of replicates has been steady at 160. So like the last 20 years, it's been at 160. But there were earlier years if you go back all the way to the 90s, where there were fewer, I think, than 160, and that's problematic because you can't specify a different number of weights, and so that's problematic. But as long as the number of BRR weights are the same, it's not a problem. But if that changes, it could be problematic. So I can't predict the future of how the census will create the BRR weights going forward. But for a 10-year period, they're going to be fixed. So for the next, starting in 2016 to 2025, there's 160, and then presumably in 2026, when it changes, from what I understand, the census will keep it at 160 and it'll be fine. But if they changed it, that could be problematic. So disadvantages though to Taylor series, you do need to know the sample design. You need to be able to specify it in the procedure, so you need to be aware of how to do that. Not necessarily challenging, but if you don't know anything about the design, that could be a little bit problematic. And then, as we'll talk about more of this file manipulation. I mean, it's not a small thing, but so you need to be aware of it. And then the 2016 issue, just again something to be aware of. BRR is technically better for disclosure avoidance because you don't need to specify the design. You don't need to know anything about it. All that can be embedded in the replicate weights. So for surveys that are concerned about disclosure avoidance, BRR is definitely a superior approach. It is on disadvantages. It can be computationally a little slower, a little bit more challenging in SPSS if you don't have the macro. And it is not available on the concatenated file. So you have to download each individual year. And again, if you're pooling years, again, just that you can't pool years that have more different number of replicates. Okay. This is, I'm not going to walk through this because this is just pure repetition, but I did want to have a slide where I'll just sit here for a minute and let you look at it. But I did want to have a nice slide that just sort of just ran through everything there and sort of summarized the different features of each of the three methods on one sort of slide. And you can sort of see, I mean, each one has checkboxes, and I wouldn't say, oh, TSL has more checkboxes, so it's the best. Was not my intent when I was putting this together at all. I was just going through different features, but they each have their pros and their cons. And I think the key key message that I'm trying to get across here is they just need to be aware of them and know how you like to analyze data. And once you understand that, I think that will help lead you to the approach that's best suited towards you. Because I don't think any of these are bad ways to go. They're just different. And so it's really what works best for you and the way you like to analyze data, and in particular analyze the NCBS. So I don't think any one of these is better, or I wouldn't discount any one of them per se. Okay. Last, in this section, I just wanted to show you, just so you can understand how the estimates are different. And I have 2 years here, 2020 and 2021, and I have all the types of violent crime and then personal theft. And the numbers in the table here are what's called the relative standard error. For those who don't know what a relative standard error is, it's the ratio of the standard error that you get over the point estimate times 100. So it's a percentage. And so this is a measure of how the quality of the precision of the estimate. So the problem with just looking at standard error is that it's relative. How good it is relative to the point estimate. So you might have a big standard error, but if it's a big estimate, it could be relatively small. So for relative standard error, smaller is better. So smaller relative standard errors mean has better precision. And what I'll just note here is that so this is why I said there's no one that's necessarily better. It's not that there's one that's consistently higher. So the GVS, for example, if you looked at the robbery row, you'll see in 2020 it had relative standard error that's higher than BRR or TSL. But then you go to 2021 and the robbery relative standard error is lower. So going from year to year, so there is no, if you ask me, well, are GVFs always higher or are they always lower? The answer is it changes. So because it's a different model each year that's being fit, and how well that model fits for different outcomes is going to vary from year to year. BRR and TSL are going to be closer to each other because they're using direct variance estimations. While they're different, they're still similar. So they're going to be much closer to each other in terms of their numbers, their relative standard errors. But as you can see, they're not exact. But the GVFs, because sometimes you're above the regression line, sometimes you're below, are inconsistent in terms of being higher or lower, and it'll vary even within outcome from year to year. So just be aware of that. Again, so just to my point that I can't sit here and say one is superior to the others, because it varies from year to year, and it's really there are pros and cons to both approaches. Okay. So at this point, I think I'm going to pivot to showing an example. And I'm going to show an example using BRR in SAS. And then Erica is going to show an example of doing Taylor series in SPSS. And so I will demonstrate this. I'm not going to run SAS live. I have code here that I'll show you, but I've sort of broken down the process into 4 steps. And I'll partially show step 1, and then I will show you the code for the other 3. But the first step is the most data manipulation, but you need to download all the data sets you need. So BRR, as I said, it's not on the concatenated file. So if you're using multiple years for your analysis, you need to make sure you set all those data, download from ICPSR, all those different data years, and set them together. And then you need to create the necessary derived variables that you need for them. So if you're analyzing certain outcome types, you need to make sure you define those, or domains like race, ethnicity, make sure you define that the way you want, and things like that. And that's step 1. Step 2 is sort of a critical step. You need to then summarize the incidents. On the incident file, you need to get summary counts of the number of incidents that occurred per person or per household, because you're going to merge those then back onto the person or household file. So in the incident file, as for those users of the NCBS know, it's an incident level file. It's not a single record file. So if a person had multiple incidents during a year, they'll be listed multiple times. And so you need to summarize that count, and then merge that count back onto the person or household file where there's only 1 record per household or per person. And so you need to merge those counts back onto it. And so that's what step 2 is. It's getting those summary counts, and then you got to merge them back on. In step 3 for SAS, you need to then, once you've got those counts, you need to divide them by the weight in order to get the accurate count for either a total or a person. You need to create an additional function, additional value, which divides that count, that weighted count that I just told you, summary count of incidents by the person weight, total person weight, or divided by the person weight, and then multiplying it by 1,000 per weight. So you need to do that in a data step, and then you can run it through the survey procedure for SAS is proc survey means. So survey means, so there's a proc means that would get you the wrong values. Proc survey means, because as a survey there, is accounting for the complex survey design, and that's the procedure you want to use in SAS. Okay. So walking through that here, and I know some of this is small, so I apologize. But you'll see, so I just have some comments here, like comment up here at the set function to see this A, and that corresponds over here to my comment annotation. So A, just this, I've already set all the years together, so I'm just noting that, but it's not a single file of incidence counts. You're going to need to set multiple years for BRR. Here in B, I'll just note here's where the definition for things like rape and sexual assault, robbery, overall assault, simple assault, aggravated assault, etc. And then the aggregate violent crime, which is the maximum of RSA robbery, yes, no, for those, and then personal theft. So these are just, you're defining your outcome variables. We're putting in exclusions. BJS typically excludes crimes that occurred outside of the United States. So that's this extra line right here. So function E, and so that's basically setting up and defining your variables. So that's the part of step. I didn't show you all step 1 with all the concat setting and stuff, but defining some of your outcome variables there. Step 2, the part of step 2 I'll show you is where you were summarizing. So here we are just using a regular proc means because we are just getting a regular count. We're not calculating a variance here or worrying about it. We are just summarizing down the variables of interest. We're using a weight statement here to get the series weight, which again was the product of weight Vicky and the series weight. That's what the series weight here is. And we're outputting that, and we're out, so we're summarizing the counts, the weighted counts for all those outcome variables that we defined in the prior slide. Okay. Okay. Step 3, I know stuff is smaller still, but step 3 is then the process of creating the variables you need for analysis. And I'm focusing here just on violent victimization. We use arrays. You don't have to use arrays in SAS, so they're a little complicated for you, in Durham. But basically, this is just looping through the different outcome types, and it's dividing it by the person. You're dividing by the person weight and multiplying by 1,000. So this violent 2 will be used for rates, and the one and taking the count the weighted count that you had divided by the population count without multiplying by 1,000. That's the variable violent 3. That's what we'll use when we want to calculate the totals in proc survey means. So that's sort of the key takeaway here. For each of these outcomes, we're dividing by their weight to then either and multiplying by 1,000 if for rates to have it be in the structure it needs to be for calculation of weights, or a calculation of the estimates itself. Okay, so now 4A is the rates. This is the function. This is the proc survey means. This is the main function. This is how you would set it up if you're running calculating rates. So first, the variance method. So you don't need to know anything about the design, but you do need to say what variance method you're using. And we're using BRR phase, and then you need to put this in parentheses phase. That's not a comment. That's how you would write it in SAS. Phase method, it divides the weights by 2. I mean, that's a little bit in the weeds, but the point is, if you just said BRR, which would run, that would get you the incorrect variances. So with the NCVS, it's really critical that you do put that in parentheticals next to it. That's what is necessary for the NCVS. Our outcomes that we get here, the mean here under that mean and some weight, we're getting the mean, which will in this case will get us a rate, and then the sum weights is the population total. Those are our outcomes that we're going to calculate. The variable violent 2, so that was the one we calculated for rates that had the multiply by 1,000. We could list other variables here. So if we wanted to get the rates for RSA, like we had that for rape and sexual assault, we had that RSA variable. So we could get the detailed ones here. We could just list them all. So you don't need multiple you could just in a row put all those variables in this bar statement. So there's no need so you could, like as I said, nice thing about this, you can calculate all this simultaneously. We are gonna then by domain get our estimates by year. And so our domain is year. If you wanted to look at other domains, so you could look at if you had calculated like age categories, like say you had 5 age, you had like an age cat variable, you could put year star age cat in the domain, and that would calculate by year and age category. That would calculate them. Or if you wanted to pool your years and do it by age, you would just say age cat. So you could put all that in your domains, multiple domains, and calculate that. To get an output data set, proc means, survey means doesn't automatically create an output data set. You do need to use the output delivery system, ODS, to get that. So you need a line ODS output, and then we create the data set. In this case, we call it estimate or est. So you do need that ODS statement to get an output data set. I mean, there will be output that populates in your output window, but if you want to get an actual data set and then use it later, you need that ODS statement. Weight, so again, in SAS, or any statistical procedure, you only can enter one weight. So we moved over the weighted incidence, so we don't need the incident file anymore for purposes of direct variance estimation. And we can just specify, in this case, if we're looking at violent crime, we can just focus on the person weight and use it. And then the replicate weights, and then we just need to specify the replicate weights, for the person 1 through 160, and we don't need to list them all out. So if there's 10, it doesn't really matter if there's 10 or 300, which I've seen 300 too, because you can just put a dash and then list them. So you don't have to, so you don't have to tediously type every single one of them. You can just put the range as long as they all have the same basic root, and the only difference is the number at the end. So the weight name is the same. The only difference is the number at the end, 1 to 160. Then you can just put a dash and list them all. So this is the survey means function for a rate, and then looking at the outcome, you'll get outcome that looks like this. So we fed in when I created my data set, I fed in years for 2016 through 21. So as I noted, I put 2016 on purpose because I want to just remind you that BRR can create proper estimates for 2016. Taylor series, we would not have been able to do that, but for BRR we can. And so we get our 2 outcome measures. We get the sum of the weights. That was that sum weight function. We get the mean. This is the rate. So 19.66 here in 2016 is per 1,000 persons. And then we get the standard error of the rate. So the standard error of the 19.66 is 0.897. And so that's the standard error. And if you want to get a confidence interval, you can multiply this number by 1.96 to get the half width, and then plus or minus, that number. And so that's the output that you would get. there are some other parts of the output, but you can, for the most part, ignore them. I mean, they help you know that things ran properly, but they're not necessary in terms of the outputs itself. Now, quickly, I'll just say in 4B here, this is just totals. The only difference in this slide is in the var statement. It says violent 3 instead of violent 2. But otherwise, the setup is exactly the same. And you can see then the difference here is that your sum is now for violent 3 is now the total. So 535 million. Wait, am I doing that right? No, so five. Yeah. Anyway, I don't see the comments. So it's hard for me sometimes. But anyway, this is the total number of violent crimes in 2016, and this is the standard error for that. You can see that. And these numbers I checked. I mean, all these numbers will match what's in the BJS crime victimization bulletins. But there's your outcome. So with that, I will pass it to Erica so that she can give you an equivalent example of Taylor series in SPSS.
Okay, thanks, Marcus. What I'm going to do here is run through some SPSS syntax that will be using Taylor series linearization to generate rates and standard errors. And with this example, I'm going to be showing how to generate rates of violent victimization per year from 2017 forward. As Marcus said, you can't do it for 2016, so I'll just be looking at 2017 forward. And it's a few steps. Majority of this code is just set up for the file. Once you get through setting it up, running it and actually getting the estimates is actually a very short set of code. Right now, you have to start with the concatenated incident level file. This is a full file. You can use a shortened version selecting certain years, but you have to be very careful that the same number of years you select here will be the same number of years you select later on in the code. First, we start with the concatenated incident level file. We exclude crimes that occurred outside of the U.S., select year greater than or equal to 1993. These are recodes that we use within our own unit that create a lot of variables that we use on a regular basis. New weight creates like incident level variables. TOC, that's our type of crime recode, and demo is like a demographic that has all of our basic demographics that we have. After that, we have to identify cases with violent crime, and new off, which was created in our TOC recode. Let LE4, that those are all of our violent crimes, values 1 through 4. So we get those cases and we get the series weight, that value for that case, and identify it in the incident level file. We also create a weight, an adjusted weight, actually based on our new off, which is our new off variable, which comes from the TOC recode. This is based on all of the person level crimes. Since violent victimization is a person level crime, we need the victimization weight for person level crimes, which includes the violent crimes and personal larceny. So new off LE5 gets all of those violent crimes and personal larceny, and getting that incident weight, the victimization weight for those cases. And we sort the cases by person ID and year quarter. This is very important. Later on, you'll see that is necessary to have these cases sorted for just every data file in this code. Now, we also have to create a victimization summary file from that incident file. So using that same incident file that was created and saved, we do an aggregation and get the number of violent crimes, that total violence variable, the number of violent crimes for each person ID and year quarter. We have to have that for each in order to get the total number of crimes that a person has had during the year. and during the quarter. We have to have that, and we also have to sum up the victimization weight to make sure that we have the correct weights when we get ready to merge and also get ready to analyze the data. This code actually saves the victimization summary file, and we have to get the file and actually open it. We open it. There's an alter type here that has to do with our merging that's going to take place in the next step. The variables that are used to merge have to be the same type. So you have an alter type command here for the person level identification variable. Now we're also here, we're sorting cases. Again, we have to keep sorting cases or else the merge that occurs in step 3 will not happen. You will run into an error. Now, in step 3, to merge the victimization summary file with the person level population file, you have to do this because SPSS can only process a single data file at one time. Therefore, you have to merge the incident level file with the person level population file into a single file in order to run the Taylor series linearization. So here we get, this is our concatenated person level population file, selecting same years. We're still sorting cases, saving that sorted person level file. And down here with the match files, it's pretty important that you do the files in this order in SPSS, or else you will run into an error and there won't be a merged file. The file statement states that is for the population file, for the person level population file, and the table statement, that has to equal the victimization summary file. If you get those mixed up, you will have an error. Also, year, the ID per and year Q variables, they have to be there. These two data files have to be sorted by those two variables, or else the merge will not work. You will run into an error. We're saving the merge file. Now moving to step 4, we create what's called an victimization adjustment factor and the actual rate variable. So getting that first, getting that merged file from step 3, we recode that victimization, that violent victimization variable and the weighting variable, because when we merge the victimization summary file with the person level file, there will be non-victims in that merged file. And SPSS, when they do a merge and there's no data for a case on a variable, it automatically makes it system missing. This code actually changes the system missing to 0 and keeps everything else. There's a victimization adjustment factor. It divides the person incident weight that was created back in step 1 and divides by the WGT-PERCY, which is the person population weight that's on the person level population file. When you did the merge, it carried it carried the population weight over, so it's on the file. Now we have to calculate a rate variable. We have to use the victimization adjustment factor, multiply it by the TV sum, which is the violent victimization count, and multiply it by 1,000 because that's how we present our rates in our BJS reports. That was the total violent victimization rate. And generating rates is our last step. You have, like Marcus stated earlier, you can't just use SPSS, regular SPSS, and get these rates via Taylor series linearization and get standard errors. You have to have a complex sample. You have to have a way of acknowledging the complex sampling design of the NCBS. So SPSS does have a complex sampling package, which is a set of commands that will allow us to take into account the NCBS sampling structure, sample design, and make it so that we can accurately reflect how the sample in the NCBS is structured. So in order to do that, we have to in order to do that, first of all, SPSS has to have the complex sampling package installed with your version of SPSS that you have. If you don't, then these commands, the CS analysis and CS descriptives, this code will not work. First, you have to create what's called a complex sampling plan. This is where you tell SPSS how the sample is created, and it uses variables. First of all, it has to be run over the data file that you want to get the rate from, which for us will be that combined incident person level population file with all of the rate variables and victimization adjustment factor and all of that. That's what it has to be run over in order to be created. It can't be created like without a data set. The analysis weight would be, since we are looking at a personal victimization, which is violent crime, we need the person population weight, which is WGT-PERCY. We have two variables here, the pseudostrata and the half sample variables, B2117 and B2118. Which have to be used in order to create this sampling plan. And next, finally, is to actually generate the actual rate. What I'm doing with this code is generating rates of violent victimization from 2017 to 2021 over that merge file that we created earlier, using the complex sampling plan that was done above this plan right here, this created by CS plan analysis, and also using the rate variable that was done above. Here I'm selecting, since I use the full concatenated file, I am selecting the year to be 2017 going forward. This plan file, this is the plan, and it has to be here. This is the plan that was created earlier. This TVRT, this is the rate variable that was created earlier. You have to have a subpop table if you're doing annual rates with the concatenated file, because if not, it will just give you estimates for the entire table, which is like an average of all, the rate would be the average of everything, of all years that are in the data set. So here we have to have a year layering it so that we can get annual rates going from 2017 to 2018. And with statistics, we have SE, which stands for standard error. And now I'm going to run this to show you the actual standard errors. And it will take a minute because we're running it over the full concatenated files. The person level population file is the largest file that the person level population, the concatenated file is the largest file that we have. So it takes a while to run it. So if you want to just run it for a year or so, you can actually cut down the incident level and the person level files to whatever year you're working with, except for 2016, and merge them together, and it should be able to take a shorter time to run. Now, this SPSS output, it shows that complex samples, this is the descriptive output. Now this univariate statistics, this is what I was talking about earlier about creating a mean across all the data. This is the rate for all of the years that I had selected from 2017 to 2021. This is an overall rate. But here are the annual rates. One for each year. We have the rate, the estimate, these are the rates, and the standard error. And if you notice, these rates are the same as what you would find in here. Table 1, this is Table 1 from the 2021 Criminal Victimization Report. The rates that you would find there in SPSS are the rates that you will find in this first row of the table, the 20.6, 23.2, 20.0, 16.4, and 16.5, the same rates. And I will stop sharing. And I think at this point we are ready for our Q&A section.
Yeah, thank you, Erica and Marcus, both for those demonstrations. So we can go to Q&A. I don't see any currently. Let me just check the chat. I don't see the chat, any questions in the chat. I don't see any questions in the Q&A so far. I'll give maybe people a moment to write some in. I know it's a lot of information today, so definitely we'll display our emails before we log off in case you have any questions that you think of after the presentation. And one other thing I wanted to bring up was when Marcus was talking about the GBFs, the Census Bureau does create GBFs specifically for the NCVS, and GBFs for each year are available in the code book, which is available through the National Archive of Criminal Justice Data, NACJD. So if you go to NACJD to download the public use file, that should come with a code book, and within the code book, there's a source and accuracy statement from the Census Bureau, which contains the GBF parameters if that's the method that you wanted to use. And then with anything related to the NCVS when you're generating your own estimates, if you're wondering whether you're doing something correctly in your own calculations, some of the easiest ways to check are just comparing against published reports, kind of how Erica showed during her section. You can look at Criminal Victimization Bulletin and check the estimates are calculated correctly and check the standard errors. On the bulletin, in that particular bulletin, we did use BRR rather than TSL, but maybe, you know, sometimes different publications use GBFs or BRR depending on what was available at that time. So I wanted to throw that out there for anyone who might be thinking of projects that they're working on.
I think one question has now come in.
Do you see it, Marcus? I don't see anything in the Q&A.
Oh, yeah. So the question
panel.
I see is, so what if one has a regression model? Which procedure should one use? So the GVFs are only for descriptive statistics. So there aren't GVFs for regression models. So in that case, you would have to use one of the direct variance estimation methods. So you can use those. You can use either Taylor series or BRR for a regression model. Proc survey means would not be your function. I think in SAS it's proc survey reg and if you have a dichotomous outcome, I think it's like proc survey logistic. So there are survey procedures for regressions in SAS, I know, and I imagine too in SPSS, but you would have to use one of the direct variance estimation procedures. Either one will be allowable. And so the second question I see here is, can R also be used? Well, yes, we just gave examples in SAS and SPSS, but R has complex survey functions as well, procedures and functions, and you most definitely can use R as well. Yes. Yeah, Sudan is another software package out there that I know will work. Stata, if people are Stata people, any of those software packages that can account for a complex survey design, as long as the procedure you're using is a complex survey procedure, and R, Stata, Sudan, SAS, and SPSS all have those, so you can use any one of those. We were just limited in time and what we can show examples. There are actually examples on the BJS has published a user's guide. There are user's guides to direct variance estimation that are out there and you can get it through Google. There's a Google search. There are appendices, and I know we did it in we did Sudan, SAS, SPSS, and R. So there are examples out there too. So there are example code out there that BJS has published.
Yeah, I think it's under the National Crime Victimization Survey data collection page. I think there's like a document subsection that I think those are under, if I remember correctly.
Yeah, and that document will also talk through how to merge the files that you need to do. So it'll walk through that, and then there are appendices for each of the different software packages with examples how to do this.
I don't see any other Q&A questions on my end. If any of the other presenters got one that I didn't, feel free to speak up. If that's all the questions, if you think of anything after this presentation that you didn't think of now, all 4 of our emails are displayed on this screen. We're happy to answer any questions that we can. And thank you again from both BJS and RTI for attending this webinar. We hope it was helpful and that you're now thinking of all the great ways you can use the NCBS data to learn more about crime in the US. So thank you again. And I think our emails are also, Tammy posted our emails in the chat as well. And I hope everyone has a wonderful day. Thank you again to the panelists and everyone for attending.